All right, so this is motion graph conversion practice B, and it says on the graph above, draw a position versus time graph showing the following motion. So I'll draw my position versus time graph. It looks like I've got 10 seconds to look at, so I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I need to think about positions that it looks like it starts at +3, it goes to position 0, and then -5. So I'm just going from +3 to 5. So I think what I'll do for my position is I'll say this will be +1, 2, 3. That'll give me a nice lot of room to work with. This will be -1, -2, -3, -4, -5. That's pretty good. And okay, so from 0 to 2 seconds, the object moves from position +3, that's there, to position 0. That's from 0 to 2 seconds, and it does it at a constant speed. Constant speed on position versus time is a straight line. So here's my straight line. Right? From 2 to 4, the object doesn't move at all, so it stays at position 0. 2 to 4. From 4 to 9, it goes from position 0 to position -5. So at the end of 9 seconds, I'm located here at -5 meters. And it does it at a constant speed, so that's going to be another straight diagonal line. And then from 9 to 10, it's motionless. So that's going to be another perfectly horizontal line. So there's my position versus time graph. For my velocity versus time graph, I'm going to make sure that this is right below it. I'm looking at this and I'm seeing it's only ever moving in the negative direction. So I'm going to leave a little bit of space at the top for positives, not because I need them, but just because it'll help kind of clarify that where things are and how this thing is moving. But this will be my velocity, and this is going to be 0, and I'm never going to have any positive velocity. Some of you might have looked at this and thought, well, it's in the positions are positive, so that must be positive velocity, but it's not. Positive velocity means that its position is becoming more positive. This is negative velocity, and so is this. And then I need to think about my slopes, because that's going to determine the magnitudes of velocity that I need to put in there. So for this one, I drop 3, that's -3 in 2 seconds. So that's 3/2, so that's -1.5. So this has a slope of -1.5. This has a slope of 0. This drops 5, and it does it in 1, 2, 3, 4, 5 seconds. That was nice of me. That's going to be a slope of -1, and this will be a slope of 0. And these slopes tell us the velocities. Since these are straight lines, the velocity is the same throughout all of these sections, which means my velocities on my velocity versus time graph are going to be horizontal lines representing constant velocity. The largest velocity I have looks like it's 1.5 meters per second. And so I can make my scale pretty large here. I'm gonna say, let's do like 2, 4, 6, 8, 10. This will be -1 meter per second, and then 2, 4. Here's my -1.5 meters per second. That's gonna allow me to have a nice big scale to look at. And I've got the times should match up here. And I'm going to write them up here just because this is a large enough screen that I can't quite see them. So this will help me make my graph. And now I'm going to draw my velocities in. So between 0 and 2 seconds, the slope on my position versus time graph was -1.5. So my velocity should be -1.5 horizontal line. From 2 to 4 seconds, I have no velocity. slope is 0. From 4 to 9 seconds, I have a slope of -1. So from 4 to 9 seconds, my slope is -1, and my velocity is -1. And then from 9 to 10 seconds, it's back to 0. Now I connect these lines like this, and this is my velocity versus time graph. Okay. And then we need to do some calculations. So it says for number 3, use the velocity versus time graph to calculate change in position from time 1 to time 6. So that's going to be this rectangle and this rectangle. There's no triangles, so this will be easy math. This is going to be 1 times -1.5, which is 1.5 meters in the negative direction. This is going to be 2 times -1, which should be -2 meters. So from my velocity versus time graph between time 1 and time 6, I should have moved -3.5 meters. And then the next question is, do the same thing, only use your position versus time graph. So let's see what we get. At 1 second, I should be located right here. This is positive 1.5 meters. And at 6 seconds, I'm located right here. This is -2 meters. So I went from positive 1.5 down to 0, that's -1.5, and then an additional -2. So it looks like my displacement from here is going to just be -2 minus 1.5, which is -3.5 meters. And number 5 says, compare your answers. Well, this is the same motion. What we should expect to see is the same displacement. Will it always be the same? No, because if you have some estimation in there, if you have any approximation, then one of your graphs might be more accurate than the other. They both might be inaccurate, you just won't know for sure. In this case, we didn't have to do any estimating. We had exact numbers. We knew exactly what the numbers were. So it makes sense that these numbers would be the same. In general, what you can do by comparing these numbers is what I just showed you when we were going through the lab, which is you can refine your whatever it is that you're doing. Like in this case, we're making predictions of what graphs would look like. We can refine our predictions. And in this case, the fact that I got the same displacement calculated for both of these graphs, that gives me some confidence that I did it right. And just as an aside, like I wrote this problem and I did it last year, but I haven't done it since, so I might have made a mistake somewhere. It's quite possible that I've made a mistake here, but I feel pretty good about what I've got, given that it's internally consistent. Okay. So if you had a chance to look at this,